Good morning, my dear students. Okay, today in this lecture I am going to start a new module, that is module number 2. Okay, so normally this chapter deals with what the finite element formulation of one dimensional element. Okay, second dimensional element. Okay, that includes what linear and higher order elements. Okay, and also they are introduced some numerical integration and the using Gauss elimination quadratic model. Okay, so here so far what we studied is one dimensional element. Okay, that is each node having 2 degree of freedom. Okay, so in this section we are going to study about the analysis of bar, that is analysis of axial forces, tapered bar problem. Okay, truss element. Okay, all those things we are going to study here. Okay, so the normally the one dimensional elements are used to reference what the axial bar, spring, trusses, beam, like member for a finite element analysis for the purpose. Okay, so here such elements we are going to call as what the which is useful to analyze the axial bar, truss, cable or frame structure, many more. Okay, in the civil structure also, that is well construct in the building everywhere. Okay, so such structure tends to what we have to well define the terms of a number of type of element which are going to use. Okay, how many elements we are going to particular we are going to fix that particular bar we are going to study in this module. Okay, for example, if you take if to represent a truss element. Okay, in a for the truss element, what each node having what a 2 degree of freedom. Okay, that is a linear element. Okay, which is sufficient to get the accurate result in the this ANSYS software. Okay, so however, even if you look at that, okay, for example 3 bar node element. Okay, the each element will be having the suitable in the case of 3 bar element. Okay, which will have what more suitable in case of analysis of a cable structure. Okay, to capture the non-linear effect, all those things. Okay, so here we are going to study about the in details. Okay, so that is about the this module 2. Okay, so in module 2 same problem. So here we are going to study about what the derivation of stiffness matrix. Okay, and what are the different what are the assumptions we are going to made in that stiffness matrix. Again, what are the importance of stiffness. Okay, analysis of one dimensional analysis, 2D analysis. Okay, well, like for example trusses, bar, all those things. Okay, along with this they are include the analysis, that is formulation technique. Okay, formulation nothing what here this linear interpolation polynomial in terms of local coordinate for the one dimensional, two dimensional and higher order interpolation function for the first quadratic and cubic element in natural coordinate. Okay, constant strain angle, 4 noded tetrahedral element. Okay, that is shortly called as tet 4, 8 noded hexahedral element, that is hexa 3,8 and 2D, and along with that isoparametric element, Lagrangian interpolation function. Okay, all those things you need to study in this chapter. Okay, so this model consists of 2 sections, that is one is introduction to stiffness matrix. Okay, and this and the last is both are same only, and this is little bit different. Okay, so here they are repeated. I think here the one dimensional element analysis for bar and truss, here also they given. Okay, so here you need to calculate in the all the problems, you need to calculate the displacement, stresses, reaction. Okay, each node. Okay, so in this let me okay, so we are going to study this about what the module 2 syllabus. Okay, so as compared to these two sections, this first and third section is very easy. Okay, we can attempt in the examination. It is little difficult. Okay, so this cannot what here we will do this. Okay, but it is difficult as compared to this section. This is little difficult. Okay, you have to do this. This is very simple. Okay, so that is the first section, that is stiffness and numerical integration. Okay, so coming to the what you mean by stiffness. Okay, let me understand for stiffness nothing but what if you take any bar element or spring element, what do you mean by stiffness? Stiffness nothing but what force per unit deflection, that is called as a stiffness. Okay, I wrote here the stiffness. Okay, stiffness nothing but what force or load per deflection, that is called as deflection. Okay, so the normally it is denoted as what capital K is equal to force into displacement. Okay, U, so U stands for the displacement. Okay, some books they are denoted as what Q. Okay, so formally force is equal to K into U. Okay, so this formula we are going to use everywhere to formulate the this bar element. Okay, stiffness, this what truss element problem or this beam element problem. Okay, so look at this. This is a consider this figure shows what a spring element. Okay, one end is fixed, another end is force is acting. Okay, if you extend, if you apply a force external, that is a tensile, this spring will be displaced some distance. Okay, that is what the displacement, that is denoted as U here. Okay, that is K is equal to force applied by deflection, that is displacement. So force is equal to K into U. Okay, for example give equation number 1 for this. Okay, according to the Hooke's law, we have the consider now bar element. Okay, so this is a bar element. Okay, so this is the length and this is the area, cross section area of the tank. Okay, if you apply a force here also going to displace some position. Okay, okay, that is what denoted as U. Okay, so according to the Hooke's law, the stress is directly proportional to the strain. Okay, stress is equal to where some constant is Young modulus. Okay, so we know that stress is equal to what Young modulus into we are after this stress is equal to A into epsilon naught, that is a strain. Okay, stress is equal to force per unit area. We know this force per unit area. E is equal to this. Okay, E nothing but what change in length, strain nothing but what change in length by original length. Okay, this change in length U and original length is L. Okay, so again you resimplify this, P is equal to AE by L, you are going to get. Okay, so this P by K, P by this what this k. So p by u is equal to what from this equation? P by u is equal to k. So substitute k is equal to this, you are going to get k is equal to ae by l. Okay, this equation you are going to use in upcoming while solving the problem. This is very important. Okay. So this is about the element stiffness matrix. Okay, so now coming to the derivation. So this derivation is very important for the point of examination. Okay, so derive an expression for element stiffness matrix for 1D bar element using two methods will be there. Okay, so one is minimum potential energy method and one more is a direct method. Okay, in examination nothing is mentioned means you can use any one method. Okay, that is show that the element, otherwise they may ask you like this. Okay, show that the element stiffness matrix for 1D bar element that which is denoted by k is equal to ae by le 1 minus 1 minus 1 1. Okay, this formula is most important to calculate the stiffness matrix for what? So bar element. Okay, so one dimensional bar element. Okay, this is, you have to show you have to derive this equation. Okay, throughout this FEM you are going to use this equation. Okay, so that is what by you have to derive this equation with the help of minimum potential energy direct method. Okay, so now question is they may ask you like this, expression for the element stiffness matrix for 1D bar element, not truss element. I am talking you 1D bar element. Okay, one dimensional element problem only. Okay, 1D bar element using minimum potential energy. They are asking with the help of minimum potential energy you need to derive the stiffness matrix for 1D bar. Okay, consider a bar. Okay, so this is a bar element is there, one end is fixed, another end is force is acting, that is axially. Okay, at node number point, this 1 and 2 are the node at, okay, at node number 1 displacement is u1 and at node number 2 displacement is u2. Okay, if you apply a force some displacement takes place. Okay, that if that is x, okay, it will touch some distance. Okay, okay, so bar under axial loading. Okay, at the same diagram you have to draw the FEM model. Okay, this is what FEM model. So this is a element. Okay, this is a bar element. So L is the length of element. So here the force 1 will be acting at node number 1, displacement is u1, at node number 2 is force is f2, displacement is u2. Okay, this is a FEM model. Okay, so now we know that if you want to minimum potential energy, what already we studied in the first model, potential energy is equal to what? The sum of the strain energy plus work potential. Okay, yes, strain energy plus work potential. Work potential it is due to the external forces acting, okay, on the particular element. Strain energy nothing but it is a stored energy in the given bar element. Okay, you have to now substitute these values. Okay, so strain energy for the bar is, we have the half of the integration of 0 to L ae dou u by dou x whole square into dx. Okay, this is the energy which is stored in the given bar, and work potential formula is not, it is due to the external force. Okay, here the how many forces are acting in this problem? Two forces. Okay, one is at node number 1, at node number 2. Okay, so work done by the external force we are going to consider here negative. Okay, so work potential is equal to minus f1 into displacement minus f2 into displacement. Okay, so that is f1 u1 minus f2 u2. Okay, substitute those strain energy and work potential value in the equation by potential energy equations, you are going to get this equation, that is pi is equal to ae by 2, so 0 to L dou u by dou x whole square dx minus f1 u1 plus f2 u2, give equation number 2. Okay, but after this assume polynomial function. Okay, since the given problem is a one dimensional element, so assume polynomial function for the 1D order element is equal to what? U is equal to u0 plus a1x. Okay, give equation number 3. Okay, so now which we need to calculate the dou u by dou x value. So how to do this? Okay, applying the boundary condition. Okay, so which should be satisfy the following boundary condition. Okay, so here at node number 1 x is equal to 0, u1 is equal to 0. Okay, so x is equal to 0, u1 is equal to 0 at node number 1. So substitute, you are going to substitute in this equation from equation 3. So you are going to get a0 is equal to a1. Okay, coming to the at node number 2, x is equal to L, total length is at node number 2 is x is equal to L, u is equal to u2. Okay, so u is equal to u2, x is equal to L, substitute in this equation. So you are going to get a1 is equal to u2 minus u1 by L. Okay, so now you got the a0 value, a1 value. So the main purpose of this polynomial function is to calculate this a0 and a1 value. Okay, so you calculate a0 value is a1 u1, that is a1 is equal to u2 minus u1 by L. Okay, so substitute this equation in this equation, you are going to get u is equal to u1 plus u2 minus u1 whole divided by L into x. Okay, give question number 4. Okay, so now in the potential energy value is what? Dou u by dou x is there, so you have to calculate the dou u by dou x value. Okay, so to calculate, to substitute in this, you have to differentiate with respect to x for the equation number 4. Okay, so that is differentiate with respect to x with to the equation 4. Dou u by dou x is equal to what? u1 plus u2 minus u1 L into x. Okay, you have to differentiate this equation. Okay, so u1 is constant 0, so u2 minus u1 as it is, x into differentiation is 1. So give equation number 5. Okay, So now substitute that dou u by dou x value in the above equation. You are going to get pi is equal to ae by l integration of 0 to l u2 minus u1 okay whole square dx minus f1 u1 minus f2 u2. Okay, so this is a constant term, keep outside ae by 2, so u2 minus u1 by l whole square integration of 0 to l dx minus f1 u1 minus f2 u2. Okay, so this is the constant term. Okay, so apply the limit 0 to l. Okay, substitute in this, we are going to get this equation pi is equal to ae by 2 u2 minus u1 whole square by l. Okay, integration of 0 minus 1 is nothing but what, 1 into 1, this as it is. Okay, that is 1 into l, you are going to get minus f1 u1 minus f2 u2. Okay, again you simplify this is a minus b whole square formula, so a square plus b square minus 2ab. So solve this, you are going to get this equation, give equation number 6. Okay, so what is the condition to the minimum potential energy is to be minimum? What is the condition? So here two unknowns are there, so dou u by dou x1 which is equal to 0 and dou pi by dou u2 which is equal to 0. This is the condition. Okay, so differentiate with respect to equation 6 with respect to u1, so you are going to get this dou pi by dou u1 which is equal to ae by 2l 2 u1 minus 2 u2 minus f1. Okay, so f1 is equal to what, you are going to get this equation, give equation number 7. Okay, again differentiate equation 6 with respect to u2, so you are going to get f2 value, so f2 is equal to this what, ae by l minus u1 plus u2. Okay, so equation 7 and 8 can be written as matrix form, so since it is 2 forces will be there, so f1 f2 u1 u2 ae by l 1 minus 1 minus 1 1 you are going to get. Okay, equation 7 and 8 you have to write in the matrix form, you are going to get this. Okay, so this equation I have to compare to the standard formula, so what I derived in the first slide. Okay, so compare equation ku which is equal to f. Okay, where k stands for this value, that is ae by l is equal to what, 1 minus 1 minus 1 1. Okay, this is what stiffness matrix. Okay, so this is what the derivation for element stiffness matrix for 1D bar element. Like that you have to derive this equation. Okay, very simple derivation, this is most important for the point of examination. All the problems related to bar, it depends upon this formula only. Okay, so k is equal to ae by l 1 minus 1 minus 1 1. Okay, so this is what according to the minimum potential energy method. Okay, so k stands for stiffness matrix, a stands for area, e stands for Young modulus, l stands for length of element. Okay, so this is for the derivation for element stiffness matrix for using minimum potential energy. Okay, same equation we are going to derive by using direct method here. Okay, so another method, same derivation. Okay, derive an expression for the element stiffness matrix for 1D bar element using direct method. Okay, same problem, consider a bar. Okay, one end is fixed, another end is load is acting. Okay, f2, so which is stress, which at a displacement what, it will displace something. Okay, so at node number 1 u1, at node number 2 u2. Okay, length of element. Okay, under it is axial loading, same you have to build in the finite element model. At node number 1 f1 u1 with the force and displacement, at node number 2 u2 f2 with the displacement and force. Okay, so let u1 be the same I wrote here. Okay, we know the element stiffness matrix for the standard formula ku which is equal to f, so give equation number 1. Okay, so here k is equal to what, since only one element, two element will be there, so here k11 k12 k21 k22, that you have to write here. Okay, k11 k12 at node number 1. Okay, so 1 1 and 1 2 2 1 2 2. Okay, for example 3 means one more will come, that is 13 also come. Okay, suppose third element present means, third node is present means. Okay, so displacement is u1 u2 is there, u1 u2 f1 f2. Okay, so give equation number 1, give equation number 2. Okay, so if the force f1 is induced at node number 1, then the deflection u11 at node number 1 is given by. Okay, if the force is induced here, so deflection will come what, u is equal to displacement is equal to force into this. Okay, u11 is equal to f1 le by ae. Okay, so again you simplify this, force you have to by u11 which is equal to ae by l1. Okay, so this is equal to what, at k11 this value you are going to get, so give equation number 3. Okay, similarly at node number 2 opposite direction. Okay, so for the equilibrium position f1 plus f2, so f1 is equal to minus f2. Okay, so you have displacement at node number 2 is given by u21 is equal to minus f1 le by whole divided by ae by ae. Okay, so f1 again same 21, so remaining is ae by l. Okay, so but it is opposite in direction, so put minus here. Okay, so k11 and k21 you got, similarly you have to calculate the 22 and 11. Okay, that is 12. Okay, so same you are going to get same. Okay, so here nothing is there, nothing value is given displacement, same value you are going to get. Okay, get 22 and 12. Okay, so after substituting the values, so you are going to get like this, k11 k12 k21 22. Okay, substitute all the values in this equation, ae by le minus ae by le minus ae by le ae by le. Okay, so take the ae by le common outside, so you are going to get k is equal to ae by le 1 minus 1 minus 1 1. Okay, so this is the equation for what, stiffness matrix for the by using direct method. Okay, so this is very simple. So this equation you are going to use to solve all the bar element related to one dimensional problem in finite element method. Okay, so that's two method we solved. Okay, in examination you can solve any one method using direct method or minimum potential energy method. Okay, so now one more derivation is there. Same, this what we studied in the this by using direct method, same I wrote here in the in place of spring. Okay, a derivation of a stiffness matrix for a single spring element. Only this single spring element is there. Okay, same problem, instead of bar they given spring here. Okay, same procedure you have to apply here. So here consider one spring element. So here this is a spring which is denoted by stiffness is k. So I nothing but what, I and j is nothing but the node number 1 2. Okay, so here I is nothing but force at node number 1 and fj nothing but force at number 2. Okay, uy and uj nothing but what, displacement at node number 1, displacement at node number 2. Okay, so we know the force is equal to what, stiffness into deflection, that is in the mathematical equation we can write as k uy minus uj. Okay, so fi is equal to what, k uy minus uj, so which is equal to k uy minus k is just to multiply this equation. Okay, so you are going to get this, and fj at node number 2 is force, that is opposite. So opposite of this interchange you have to, this uj you write here and ui write this side. Okay, so that is what, f1 which is equal to minus f2. So because of that we are going to get here negative sign. So k ui qj minus ui. Okay, again you simplify, you are going to get minus sign here. Okay, in the matrix form you write here k minus k minus k k ui minus uj, so which is equal to fi uj, which gives what, ke u into, which is equal to f. Okay, where k nothing but what, this k minus k minus k k. Suppose otherwise you can write 11 12 12, that is this is what, 11 12, okay, 21 22. So this is what the stiffness matrix for one spring element. Okay, suppose two spring element means one more column will come. Okay, that is you have to add this to that. Okay, k1 plus k2, that is called as global stiffness matrix. Okay, so like this you have to solve the derivation for element stiffness matrix for bar element, spring element. Okay, like this you have to derive these equations. Okay, so I hope you understand this derivation. This is most important derivation for the point of examination, as well as to solve the problems in both laboratory and theory lab, that is common lab you are having. So same formula I'm going to use. Okay, so I hope you understand this introduction class in module 2. Okay, thank you very much.